Resistors are very common in electronic circuits. Have you ever wondered why they're used in a circuit? Maybe you're wondering, how do you determine the value of resistor needed in a circuit? Well, welcome to video 5 in our Basic Electronics Using Fusion series, Practical Applications and Considerations Using Resistors. In this video, we'll explain how and why resistors are used in a circuit and how you determine the value of resistance you need in a circuit. Resistors are used for three purposes in electronic circuits. 1. To limit current through devices. 2. To divide up voltage. And 3. To develop a changing voltage in response to a changing current. You may have seen this circuit before, as it is very common. The 330 ohm R1 resistor limits the current through the LED to a safe value. If we simulate this circuit, we see that the current leaving the source is 10.1 milliamps. If we remove the resistor and connect the LED directly to the power source, the full 5 volts of the power source will be across the LED, and if we select Simulate, we see that the current rises to 4.18496 amps. This is too much for the LED and it will burn out. We need the resistance to limit current in the circuit to 10.1 milliamps. Voltage dividers are series circuits that, as their name suggests, divide up the voltage. After selecting the Simulate button, we see that Fusion calculates the voltage at the top of R2 to be 1.5 volts. The remainder of the 9 applied volts is across R1. You may think that we could use the 1.5 volts to power other circuitry that requires 1.5 volts to operate. Be careful. Any additional load we connect across R2 lowers the overall resistance of the bottom part of the divider. Selecting Simulate shows that the voltage will drop to 562.5 millivolts. If you want to make sure the voltage doesn't drop significantly, make sure the resistance you add across the resistance is much higher. At least 10 times is a general rule of thumb. For example, 22K, or better still, 220K. But what if you have to connect a 1 kilo ohm load across R2? Is there anything you can do to keep the voltage across R2 and R3 around the desired 1.5 volts? Yes. Simply make the voltage divider output stiffer by lowering the values of R1 and R2. One thing to note is that this is not an efficient circuit. Most of the current is used to keep the voltage around 1.5 volts. As the ammeters show, of the total 30.24 milliamps flowing, only 5% of the current, or 1.44 milliamps, flows to the load R3. 95% flows through R2. Oftentimes in a voltage divider, one of the resistors is a sensor that changes resistance in response to another quantity. Sensors exist that change resistance in response to light, temperature, pressure, weight, to list just a few. Let's say R1 is a light-dependent resistor. The schematic symbol for a light-dependent resistor, or LDR, requires the addition of arrows that represent the presence of light shining on the resistor. Let's say that in the dark, the LDR exhibits a resistance of 500 kiloohms. So if we change the resistance value of R1 to 500K and simulate the circuit, we see the voltage drops to 35.9 millivolts. And let's say that under light conditions, the resistance changes to 100 ohms. Changing R1 to 100 and selecting Simulate shows that the voltage rises to 8.57 volts. Placing R1 alone across the power source won't work, as we would always have the same voltage of 9 volts across R1. Regardless of its resistance, we need another resistance to convert the change in current due to the change in resistance to a change in voltage. The addition of R2 provides a changing voltage in response to changing current caused by light striking the LDR. And this is the third application of resistors. Many electronic devices behave as constant current sinks. Transistors, temperature sensors are two common devices that will sink a constant current. This is the symbol for a constant current DC source. It's also the symbol for a constant current sink, as the current through it will always be constant. We've connected a resistor in series with a current source so that the circuit is sinking a constant current. In this circuit, imagine the current source changes in response to temperature. Let's say the current is 10 milliamps at 0 degrees C and at 50 degrees C is 10.5 milliamps. If we select Simulate or apply Ohm's law, we'll see that at 0 degrees the voltage across R1 will be 10 volts. And if the temperature rises to 50 degrees Celsius, VR1 becomes 10.5 volts. The 1 kilo ohm resistance converts the change in current to a change in voltage. Note that I've included a 12-volt power circuit to make the circuit representative of an actual circuit, and the current source is acting as a constant current sink. The advantage of a constant current output is that the effects of resistance of long lengths of connecting wire are removed. Notice the voltage across R1 is still 10.5 volts. The output of the current source rose to 10.921 volts in order to keep the current constant at 10.5 milliamps, with 0.21 volts dropped across each wire. Let's revisit our first circuit where the resistor R1 limited the current to approximately 10 milliamps. Why was 330 ohms chosen? Well, according to the datasheet, the LED was tested at a test current of 10 milliamps. And from the graph on the datasheet, we see that at 10 milliamps, the forward volt drop across the LED is about 1.85 volts. So we know that there will be approximately 1.85 volts across the LED, which leaves 5 minus 1.8 volts across R1, or 3.15 volts. And applying Ohm's law, R1 equals the voltage across R1 divided by the current through R1. And we want the current through R1 and the LED to be 10 milliamps, so our resistor should equal 3.15 volts divided by 10 milliamps, or 315 ohms. And the nearest standard value is 330 ohms. And we can see from our simulation that our simulation values are very close to our calculated values. Let's examine our voltage divider application and see how we calculate the values for it. The first thing we need to know is what voltage do we want from the divider. Let's say it's 1.6 volts. Next, we need to know the applied voltage across the divider. A typical voltage is 5 volts, so let's use that. Next, we need to know either the current we want flowing through the divider or one of the resistor's values. For this example, let's make the current through the divider 1 milliamp. And now we just need to calculate the resistor values using Ohm's law and/or the characteristics of series circuits. Ohm's law tells us that R1 equals the voltage across R1 divided by the current through R1. And we know voltage divides up amongst devices in series, so the voltage across R1 equals the V applied to the circuit minus VR2. Formally, this is called Kirchhoff's voltage law. Or VR1 equals 5 minus 1.6 volts. And so the voltage across R1 is 3.4 volts. And going back to our Ohm's law formula, R1 equals the voltage across R1 divided by the I through R1, or 3.4 volts divided by 1 milliamp, or 3.4 kiloohms, which leads to a nearest standard value of 3.3 kiloohms. We can revise our current through the divider to maintain accuracy, but for most applications, it's not needed. We'll do it here so our calculations remain accurate, because current is the same, and because current is the same in all parts of a circuit, IR total equals IR1 equals IR2. Formally, this is called Kirchhoff's current law. And IR1 equals V across R1 divided by R1, or 3.4 volts divided by 3.3 kiloohms, which equals 10.3 milliamps. Using Ohm's law, R2 equals the V across R2 divided by the I through R2, or 1.6 volts divided by 10.3 milliamps, or 1.553 kiloohms. And a nearest standard value of 1.5 kiloohms. And here's our final circuit. Let's simulate the circuit in Fusion and check our work. The simulation results show the voltage across R2 is 1.5625 volts, close to our 1.6 volts desired voltage. In our next video, we'll discuss power in resistive circuits.